All right, lecture 30, converting normal to standard normal random variables. All right, so I've given you a little bit of a hint that random variables come up in all kinds of practical situations. Data tend to be normally distributed with some mean and some standard deviation. But when you don't have tables for every single normal random variable possible, we would have to have infinitely many tables. We only have tables generally for the standard normal random variable, and that one doesn't usually come up that much in practical applications. So, what gives? Of what value is the standard normal random variable? Well, I have here in bold a wonderful fact. We can convert the random variable x, which is normal with mean mu and standard deviation sigma, into the standard normal random variable z, which is normal 0, 1. How do we do this? Simply by computing the x value's z-score. That is, I have an if-then statement. If x is normally distributed with mean mu and standard deviation sigma, then, do you remember how to compute the z-score? You take the random variable value you have, and you subtract the mean, and you divide by the standard deviation. So if I take just the random variable x, so remember what this is, generically, it's the outcome of some random experiment. I should say the result, the numerical result of some random experiment. And the set of possible outcomes that determine the value there tell you its probability, or in the case of a continuous random variable, you look at probabilities inside an interval, and you look at all the events, the outcomes that can lead up to probabilities in that interval. But my point here is this is a random variable. Here is that random variable. I'm subtracting a constant and dividing by another constant. The result is another random variable. It's transformed somewhat, but it's another random variable, and that random variable is normal 0, 1. All right, so that's pretty terrific. We can convert from a generic a normal random variable to the z random variable. So suppose I want the probability that x is less than some number, and I kind of debated what to call that symbol there, but I'm just going to use the generic sign for a number there. I want the probability that x is less than some number. And what I say there is, let me think of the event x less than that number. That's the same, equivalent, if you look at the notes, it's equivalent to, I'm just going to do a little algebra that will keep the same imbalance on the inequality. I'm going to subtract the constant that is the mean from both sides. The inequality here is the same as that one because I subtracted the same thing from both sides. This is equivalent to, next level there, let me go ahead and divide by the standard deviation, both sides. Standard deviation is always some positive number, so when I divide by it, the inequality stays exactly the same. So look what I have now done. I have turned this into the z random variable. That's the z-score, normal 0, 1. And it's less than, all this is some number minus another number divided by another number. It's just a new number. All right? So the event up here that is x less than this number is exactly the same as the event that the standard normal random variable is less than this new number that I've computed. Correct? So look, if I want to find the probability of that x is less than a number, I guess I can get this in right here. So, probability that x is less than some number you give me, that's the same as the probability that z is less than whatever that new number turns out to be when I compute it, right? And we know how to do that. We know how to figure that out because we've been doing a lot of that. Example. Let's look at, I think I want to fit it right here just to make sure I have enough room. Example, IQs are normally distributed with mean 100 and standard deviation 15. Find the probability that a randomly chosen person will have an IQ less than 94. If we have that IQs are normally distributed with mean 100 and standard deviation 15, like I saw last time, what we're saying is that if we let IQ represent the random variable of an IQ of a randomly chosen person, this will have bell curve, be normally distributed with mean 100 and standard deviation 15. It's supposed to be 15. Okay, well, what do we want? We're asked to find the probability that a randomly chosen person has an IQ less than 94, correct? Let's just go through what I did here. This event is this event right here. I'm going to convert it down to this. And I'm going to do it by subtracting the mean and dividing by the standard deviation on both sides of the inequality. So I'm going to say that this thing is equal to, watch closely, IQ minus 100 divided by 15. The probability that that thing is less than, do the same thing over here, 94 minus 100 divided by 15. Okay. Now what I've done is magic, because this thing right here, x minus mu over sigma, random variable minus mean over standard deviation, that's what this is, becomes z. It just automatically becomes z. That's what this is saying up here. Pretty terrific. I've turned that into z. And over here, this is just my new number. The old number, the number I was working with was 94, but now what's my new number? Do the computations. 94 minus 100 divided by 15, it turns out to be negative 0.4. Look at that. I'm looking for the probability that z is less than negative 0.4, and I know how to do this. I'm not going to put the chart up and go through it. You can do it. It turns out to be 0.3446. Yeah, okay, terrific. Let me do another one here. All right, example. In fact, what I want you to do, of course, is I want you to read the next example and do it yourself. All right? So please pause me, read the next example, and do it yourself. Okay, here we go. Adult women's heights are normally distributed with mean, I really hope you paused me, mean 63.8 inches and standard deviation 2.6 inches. Let W equal height of randomly chosen woman. I didn't say it explicitly here, but over here, let IQ equal the IQ of a randomly chosen person, right? I need to be able to say that, so I'm talking about a random variable. I randomly grab someone and test their IQ, right? Here, we randomly select, let's say, a woman, and we measure her height. And so that W is that random variable, okay? We want the probability that W is less than 66 inches. Okay, so the probability that W is less than 66, I'm just going to do the same thing I did here, which is the same thing I did over here. I'm going to take this random variable and I'm going to subtract the mean. Oh, I didn't write it in. W, do I have room here? Yeah, it's coming in. W is, if W is this random variable, it is normally distributed with mean 63.8 and standard deviation 2.6. Correct? Okay, let's use that. Random variable minus the mean, minus 63.8 divided by the standard deviation. That's less than 66 minus 63.8 divided by the standard deviation. You always do the same thing on both sides to keep the solution set, the set of values of W that we're looking for, the same, right? That solved the inequality. But magically, that becomes Z. And that just becomes whatever it computes to be, and it's what? Negative, or I have, yeah, okay, so not negative, it's 0.846, dot, 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 right? Well, our table does not go out to that many digits, so I was going to say equals, but we'll just say semicolon. Let's use the probability that z is less than. If we round there, we have to round there. We have no choice because our table won't go out that far for z-scores. So I'm looking for the probability that z is less than 0.85, and you can look that up. You hopefully have looked it up, and you get 0.8023. Okay, so the probability that a randomly chosen woman will have height less than 66, and by the way, we think of this as a continuous random variable, so I could put less than or equal to if I wanted to. Likewise, over here, I could put less than or equal to. It doesn't matter. That their height is 66 inches or below is 0.8023. Let me do one more example here, and I'll go to green. And again, please pause me. I say something here though. Before you pause me, recall that we think of the probability of some interval of values in a population as being the same as the relative frequency of those values in that occur in the population. Okay, so in other words, we can think of probabilities as percentages. So I want to do that here. So for example, what fraction of men are under 6 feet tall? That's the same thing as saying if you randomly choose a man, what's the probability that he will be under 6 feet tall? So I'm going to let M be the height of a randomly chosen man. And from last time, we had that men, that M will be, 69.5 and 2.4. The mean is 69.5 and the standard deviation is 2.4. Okay, so what I want is the probability. Understand, if I want the fraction of men that are less than 6 feet, I want the probability that a randomly chosen man is less than 6 feet. And I like this problem. I stated it this way in particular because, of course, we don't want to put a 6 here, correct? We have to be thinking of what we're doing. We have to think of the actual units of the problem. The units are inches, so we have to convert that to inches. So it's 72 inches. All right. And as I said, I hope you have figured this one out. You should have paused me and gone forward and gotten it. But I'm going to, do the next step. It's M minus 69.5 over 2.4. That's less than 72 minus 69.5 over 2.4. This becomes the probability that Z, that just becomes Z, is less than whatever that number comes out to be, and it comes out to be 1.0416, repeating. So again, we have to use probability Z less than 1.04. That's all the farther our table goes out. And what we get when we do that is 0.8508, assuming I didn't make an error. Okay. There you go, 3 examples. I hope you were able to work at least the last 2 without me. I do want to say one more thing, and that is, in fact, let me finish this a little bit. The answer is 0.8508. So let's say what we want is the problem asks for the fraction of men that are less than 6 feet tall. So we should say, 85.08% of men are less than 6 feet tall. Okay? I can state this problem up here as 80.23% of women are less than 66 inches tall. I can state this one over here as 34.46% of all people have IQs less than 94, right? So it's good to think now of probabilities as percentages in a population, which you already should have been thinking that way, but this makes it more explicit. All right.